Hello. Today we're going to talk about different types of graphs and what we might be able to learn from them. In our class, we're going to learn three basic ways of graphing motion. The first is a dot diagram, and the other two types are position or velocity versus time graphs. A motion diagram is simple enough. A motion diagram simply places a dot at a specific position wherever an object is located every second, every 60th of a second, every half a second, every 10 seconds. It's very similar to the story of Hansel and Gretel. Remember, they were walking through the woods and they would drop little pieces of corn or little crumbs of bread every few seconds so that they could find their way home. Unfortunately for them, the pieces of bread got eaten or stolen or trampled on or lost, and they couldn't make it, and so they ended up having to go to that witch's house and eventually get eaten and die themselves. But anyway, I've also seen these sorts of motion diagrams on the pavement when my car drives up, either in the summertime when it drips water from the air conditioning unit, or if your car has an oil leak, it might be dropping a drop of oil every so often on a pretty consistent basis and create a graph like this on your driveway. There are three different examples of motion diagrams listed. The first example here shows an object that has slowed down. The reason I know that is here it moved a great distance in a given amount of time, and here it moved a very small distance in a given amount of time. This shows deceleration. Here we have the exact same picture, actually just flipped, but in this case it shows acceleration. Here you've got a short distance covered in a given amount of time, and here a longer distance, and that's speeding up, or acceleration. Whereas down here we have an object that appears to be moving at a constant velocity, and the reason I know that is that the distances between the dots are basically the same throughout. And we could actually measure the velocity if we got out a ruler and figured out the distance between these 2 points and divided it by the amount of time that's been given to us. The second type of graph we're going to look at is a position versus time graph. Position versus time graphs graph the position of an object along the y-axis and the time along the x-axis. You can quickly identify where an object is at a given amount of time. At 3 seconds, for instance, this particular object was 60 meters away, and at 6 seconds, it was only 20 meters away. You can also quickly calculate the velocity of an object by measuring the change in position versus the change in time. Between the first and third seconds, this object moved from 20 meters away to 60 meters away. That's a change in position of 40 meters in 2 seconds. And so this particular object, whatever it was, must have been moving at 20 meters per second. Here's a couple of examples of position versus time graph. The first example shows an object that was moving at a certain speed and then must have sped up, which I can tell because the slopes are different. In the second image, we have the opposite effect. We had an object that was moving at a high rate of speed and then slowed down because this slope is slightly smaller than the slope. The third graph shows a position versus time graph that is, for the most part, impossible for normal objects. Because this graph has a near infinite slope, it means that the object involved must have been moving at a near infinite speed. No common objects that we understand can do that. However, this sort of thing does happen. In fact, it happens all the time and all around us. This happens within the atom when the electrons move from one orbit to another orbit. They jump instantaneously. And finally, graph D shows an object that's been sitting at rest for a while and then all of a sudden starts to move. The third type of graph is actually the most useful for us because it can tell us quite a bit about the motion of an object. It's a velocity versus time graph. Instead of putting position along the y-axis, we have velocities along the y-axis. And of course, time along the x-axis. In a velocity versus time graph, you can calculate the acceleration by finding the slope, because the slope is, after all, a change in velocity, a change in y, over a change in time. What's even cooler about velocity versus time graphs is that you can also calculate how far something has traveled, and you do that by calculating the area underneath the curve or the graph. That is, for this object, if I were to calculate this area, we could figure out how far it moved in that amount of time. Calculus has a term for this. They call this the integral. Let's look at a specific example. Here we have an object that travels for 4 seconds at a certain speed and then gradually slows down to a stop by 8 seconds. Let's draw a velocity versus time graph. On the y-axis here, we'll graph velocity, and on the x-axis, we'll graph time. The first 4 seconds of the trip, the object was moving at 3 meters per second. Then it starts to slow down, which we would show by drawing a line going down, and it stops at 8 seconds. If I were to connect all these dots, you would see the velocity versus time graph shown here. Now let's calculate how far he traveled in the first 4 seconds. Since he was traveling at 3 meters per second for 4 seconds, this gives us a very simple 12 meters. Now, I want you to notice that if we were to look at the graph and look at this particular rectangle, this rectangle is 3 meters per second tall and 4 seconds long. And if I found the area, 3 times 4, that happens to equal 12. And that is not a coincidence. We can use this fact anytime we've got a velocity versus time graph. In fact, that's how I'll answer the second question. How far did he travel in the last 4 seconds? Well, that would be the area of this triangle here. And remember, a triangle is half of a rectangle. So half of 3 times 4, half of 12, that would give us 6 meters. His acceleration, remember, acceleration for velocity versus time graphs is the slope of the line. So slope is change in y. Slope is change in y over change in x, which in this case would be a decrease of 3 meters per second over a course of 4 seconds. That would correspond to negative 0.75 meters per second squared. In our final example, we're going to revisit one of my favorite scenes from one of my favorite movies, and that is when Marty and Doc in Back to the Future are testing out the time machine. If you remember in the scene, the car was remote controlled, and it kind of started at 40 miles per hour and increased to the magic speed of 88 miles per hour. And while watching it over and over and over again, I estimated that time to be about 4 seconds. The best part about it was that Marty and Doc were standing directly in front of the car when all of a sudden it disappears into the future. What my question is how did Dr. Brown know exactly where to stand so that he wouldn't get hit? That is, how far did the car travel during this acceleration time? So, how will we answer a question like this? Let's start by making a velocity versus time graph, and then calculate the distance by calculating the area underneath that graph. So, before we begin, 40 miles per hour and 88 miles per hour. We should convert those into more standard speeds having to do with seconds. So we can calculate these pretty quickly. 40 miles per hour. Let's multiply by 5,280 feet per mile. And then divide by 3,600 seconds, which is how many there are in an hour. And if we repeat this calculation with 88 instead of 40, we get roughly 60 and 1/30. Now we can make a graph pretty quickly. 60 feet per second was the starting speed, and 130 is roughly the ending speed. We overestimated, which would be fine. I think they would rather be on the safe side. And our goal now is to find the area of this object. It's probably easiest if we break this into a rectangle. The bottom rectangle is 60 tall by 4 seconds. That's 240 feet. And this triangle here is 70 tall by 4 seconds, but it's half of this rectangle. Half of this rectangle is 1/2 times 4 times 70. That's 280 divided by 2, or 140 feet. And so the total area underneath would be 380 feet. So if I were them, I'd probably stand at about 400, or maybe not even stand in way at all. But